around there. Let's see. Yes. So I think no, I'll say that at least my father. Yeah. Two honors. Okay, let's start.
So we are already ready. Okay. Okay, so it's a pleasure to have Amaldev among us today. And so Amaldev is visiting us from IIT Goa, and he works on logic, automata, and algebra. So if you are interested in some of these areas, also of course in Goa there is no who to talk to.
Yeah, if you whenever you want to come to Goa.
So yeah, Amaldev.
All right, so I'm going to talk about conjugacy of a rational relation. So it's I know that it is a bit intimidating title, because most people wouldn't know it. I mean, in the context of rational relation, what it means and what rational relation is. So, but I'll try to make it one actually. Remove. Okay, so let's take a star. A star with concatenation, an empty word with a monoid associated. Yeah, and the binary relation, monoid just means an asset is an associated operation in which are cases with concatenation. So we have a binary relation over the monoids X star and B star, that is a subset of X star. Binary relation of this. And we say a relation is rational if it can be built out of finite subset of X star or B star using the operations of union, product, and field star. In other words, it is just saying that there is a regular expression or a rational expression which defines this relation. Okay, so let's see an example. So for instance, this is a rational relation. So I have UV, the tuple UV says that U is over the alphabet ABC, V is over the alphabet BC, and V is obtained from U by replacing a letter. So you take a word U and you replace everywhere there is an A, you replace it by B. And then whatever you get, that is your B. So I take all such pairs. That is now this is a rational relation because I can just write a regular expression or a rational expression for that. Because I can say A plus A comma B, that's a pair in S star plus B star, and B comma B and C comma C, and then I take all their sum and put a star. So whatever this generates, because concatenation is pointwise. Because A star A B comes dot BB will be like AB and BB. So, okay, so this will generate the fact. Now notice that here need not be like synchronous in the sense that it could be epsilon here instead of A, it could be epsilon here. It could be like longer and longer words. Yeah, so you can have pretty complicated regular relations. So that's all. That is the rational relation. Okay. Now, what is conjugacy? So if I have a word, I say a pair of words U and V is conjugate. If there is word X and Y, I say U is equal to X, X, Y, and Z is equal to Y. In other words, U and V are cyclic shifts. Either can cyclic shift to the left or cyclic shift to the right and obtain V from V. So for instance, ABBA. ABBA, I can take X as A, Y as B. So AB will be XY and BA will be YX. Similarly, ABB, BAB will be, I can take X as AB and Y as B. So ABB will be XY and B Y. Now, so this idea, whenever I have words UV, this X and Y are called a cut. So pair XY is called a cut of UV. There can be several cuts of a pair. For instance, if I have a word like AB, BA, I can take A slash BAB as a cut because A slash BAB and B is B, and similarly I can have ABA. So both are cuts of this word ABA. So that is. And these are critical definitions. A set of pairs is conjugate if every pair in the set is conjugate. If every pair in the set is conjugate. Now, so we will say, so deciding conjugacy means I give you a regular expression and I ask you if every pair generated by that is a cyclic shift. The conjugacy problem is a very standard problem. In fact, in group theory, there's three fundamental problems of finitely generated groups is one is word problem. I give you two words. The other is conjugacy. I give you two words. They are conjugate. And the last one is okay. I just yeah, for the benefit of others, I'll just quickly recap. Okay, so what is the binary relation? So I have A star and B star. The binary relation of a monoid A star and B star is the subset of A star plus B star. Yeah. Is that like you take set A star and B star in binary relation, and the relation is rational if you can reach out of a finite subset of A star plus B star using the operation union product with B star. Okay. And so what does it mean? It just means that I can write a regular expression for this relation. That's all it means. So this one, in fact, the beginning of automata theory is a theorem which says that finite rational subset of three monoids are exactly same as regular subset. That's not a Cleanis theorem. Because you say that regular languages are nothing but you start with finite subsets, you close it under union product and reach. So and this rational has something to do with rational subset. We don't know any that here, but that's it. So
what is the thing? Can we build using operational union product, and what's the base case?
Finite subsets.
Oh,
like you can take the generators and you can take a generator set also. Typically, we only take the generators, but in our case, it will be much convenient if you take all of our finite subsets. Yeah, because finite subset you can write to the plus.
Okay, okay.
So, okay. So, what is product? Product is concatenation. Product of the monoid. So here we have S star for B star. So product will be pointwise concatenation. Yeah. Okay. So now, just an example. So if I have this relation UV, which says that V is obtained from U by replacing A by B. I have a word U. I replace every letter A in U by B, and then I get B. So this pair can be written as a regular expression like this. I can say that A B, B B, and C. Wherever there is A, you replace by B. Wherever there is B, it remains B. Wherever there is C, it remains C. Yeah. So it's a rational. Now the thing is that this could be like this. I have taken single letters here. It could be epsilon here. It could be longer words here. So I can replace it. Another way to see this thing is by saying that I have a non-deterministic finite automata whose transitions are labeled by regular languages. So then you read a word and you output a language. That will be exactly rational expression. So there are so many ways you can do it. So ultimately, rational expressions are nothing but relations defined by non-deterministic finite transitions.
One way.
One way. Yes, non-deterministic one-way finite. Okay, so now what is conjugacy? So a pair of words UV is conjugate. If there exists words X and Y, then that U is equal to Y and U is equal to Y. So if I have a word, two words are conjugate. If I can cyclic shift one and get the other. In other words, I can have X and Y, so then U is equal to Y and Y. Okay, so here A, B, B, A, X is A, Y is B. So this is X, Y, this is Y. Here A, B, 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 A, B. X is A, B, Y is B. So B, A, B, and A, B. So X, Y. X, Y, and X. Okay, and the pair of X, Y is called a cut. So this particular division of this U, splitting of this thing, we call it. The pair of X, Y is called a cut of UV. There can be several cuts of a pair. Because if I have AB, AB, and BA, BA, I can cut like ABA and B, or I can cut like A and B. So this XY is not a cut of U. Cut of U. So A plus BAB and B is such. Okay, now the critical definition is that a set of pairs is conjugate if every pair in the set is conjugate. Yeah, the relation defines the pairs in the relation are nothing but conjugates. Okay, so so now I was just saying that conjugacy is a fundamental problem in the thing. It rotates somewhere time. Word problem, conjugacy, and isomorphism problem are the three standard problems which were introduced for studying groups.
So the XY can be different for each pair, right?
Yes, of course. Yes, for different words it will be different. Okay. All right. Let's now. If I have two rational relations R1 and R2, and if they are conjugate, then the union is also conjugate. Because if R1 is conjugate, every pair is conjugate. If R2 is conjugate, every pair. So I take the union. So, but product of R1 and R2 need not be conjugate. That means that if I concatenate, if I take a pair from R1 and take a pair from R2 and concatenate, need not be conjugate. Why? Because you take AB and BA and it's CA and AC. So here the cut will be like X will be A, Y will be B. So XY, YX. So here X will be C, Y will be B. Now, if you take ABCA and BAAC, it's not conjugate. Why it's not conjugate? Because you have to match. There is only one B here, so you have to match. This word has to start with a B if you want to match. So if you want to match this word with a B, you have to shift this A here. So then it becomes BCA, but this is BAC. So this is not conjugate. Okay. And similarly, and if this is the case, then pin star will not be conjugate because R1 star contains R1 not R2. Definition of R1 star is union over all I greater than or equal to 0, R1 R power. Yeah. So if R1 is not conjugate, then R1 star also will be. So therefore, pin star also might be. So how are we going to decide? This is our strategy. Yeah. So I am given rationalization of the rational expression. The rationalization of the rational. Now every rationalization is equivalent to sum of sumfree expression. So if I have a regular expression, I'll call it sumfree if it doesn't use plus. Okay. Now every regular expression or any monad, not just or any monad, if you power a star, any monad, it is equivalent to sum of sumfree expression. And the idea is very simple. You rewrite the regular expression after number. So originally to start with a single element of the monoid itself is sumfree, empty set is sumfree, and now assume that E and E1 and E2 are sumfree. Then E1 plus E2 you can write it as E plus dot F. Then each of these things are sumfree, and then you take this. So this will be sumfree. And E star you can write it as E, you write it as sumfree, and then you write E as E plus dot F whole star. Now this is the E star dot F star whole star. So this is also became sumfree. Now E1 dot E2 will become here E plus dot F and G plus dot H. Now you distribute, you multiply H. So this will become G, then all the way up to H. So now you have managed to write all the cases of common. So now you write, yeah.
In that each star,
Yeah.
you were talking about the three stars, there the dots are like the standard concatenation, right?
Which one? This one?
Yeah. So that is the-
No, this is the plus.
No, no, the
right.
right
Yeah.
That is the concatenation.
Yeah.
It's not the same as
Yes. Yeah. Yeah, that's a good point. Yes, this is the concatenation. Okay. Now, when you do this, there is it can blow up exponentially both in terms of number of summands and number of individual size of each summand. Because if you take A plus B dot A plus B dot A plus B n times, that is like a linear size expression. But if you write it out, it will be every pair, every combination of ABs. Yeah, so that will be like exponentially many summands. And now you can use the same idea. You put you say that that I have to witness every word, every count. I can count. So then you can actually show that size of each summand as well as individual summands will be exponential. So when you do this one, you will have exponential size expression.
No, so what you were saying is that if I have to convert any rational expression into sum of something, then there can be an exponential blow.
Both in terms of the number of summands as well as in size of each summand. But the size of the whole expression will be still big. Okay, so now the thing is we already noticed that if I have union, then individually they have to be conjugate. So now it just reduces to checking sum of sumfree expressions. This even. Yeah. Each individual ER you just check if it is conjugate. So that's it. So now we have reduced our problem to just checking conjugacy of a sumfree expression, not plus anything. Now this is how a sumfree expression looks like. So you can actually start with the standard way in which you define anything of this kind in language theory is you start with the base set, a class C, and then you have some operators. Yeah. So in this case, you have two operators. You have one operator called K, another operator called M. So you start with the finite subset of or a single word. You start with a single words, and then you apply a K. So what does K do? In the below level, whatever expressions you generated, you put a star on top. Okay, so that is the KC. Now, once you have that half level, now what you do? You take concatenate them. Yeah, you whatever expressions you generated in the previous level, you concatenate them. So that way, so what I'm saying is that if you look at this expression, E1 itself is a sumfree expression. That itself contains sumfree expression all the way down. When you reach the bottom, it will be like single individual words. So this sumfree expression is actually built using individual words using concatenation and star. Yes. And the number of nested stars is what we call star height of this expression.
And is there an order like so what is said is that you have to apply the cleanister and then the concatenation.
Concatenation alternately.
Yeah, but is it like first I apply one and
Yeah,
then
so usually, yeah, it all depends on what you're interested in. In this case, we would like to estimate the running time in terms of start height. So we will start with something where an individual word has start height 0, and a word of this kind, even is a word, it has start height 1 and so on. So working backwards, you will say that okay, you start with individual word, then you apply clean start first, then you apply monoid closure concatenation next time. Yeah.
Here, when we are referring to star height, it's the star height in a sumfree expression.
Yes, exactly. It's star height of a sumfree expression. Okay. In general, also you can talk about star height. Yes. This is just star height of a sumfree. The definition doesn't change. It's just this is a sumfree expression. Okay.
Didn't you show in the previous slide that the conjugate, that the clean star does not preserve conjugacy?
No, it does not preserve conjugacy. Yes.
So what is the question here?
So the question is, yeah, but I'm just saying that I just said that how do you see such an expression? Now we have to check conjugacy of such an expression. It is not automatic. It is not automatic that whenever each individual components have to be necessarily conjugate and so on. Yeah. So there is some check to be done. I'm just trying to reduce this general checking. I observe that it's like applying some operators one after another that I'm getting this expression. So for each individual operator, we will formulate a problem, we'll solve that, and that will lead to the general solution. That's the idea.
So what are the alphas and betas being?
Alphas and betas are individual words. EIs are some expressions themselves.
Why do you need both of them? Why not just have even star, equal star, and beta stars?
Because there could be infinity of that form.
But even can also be one word.
Yeah, it can be one word, but that is not the most general form of a summary expression. A summary expression can start with a word, then followed by a star, followed by a word, followed by a star, and so on.
So it can be say
Yeah, it can be epsilon. That's what I thought.
Because this expression is sort of insisting that you start with an alpha zeta.
No, but it can be epsilon, no problem. Alpha 0, beta 0 can be epsilon. It's just a monoid element, which is from a star plus b star. It can be epsilon. It can be any element. Not necessarily non-negative.
Just to make sure I understand this. So, so right now, given a particular expression, you now broken it up into a sum of some few expressions.
And it's applies
to if you want to check if it is conjugate.
Yeah.
You need to somehow check each of these summands.
Yes, exactly.
And
it's applies to each of the summands.
Okay.
Now, each of the summands we are going to formulate. So now let's just observe one thing. That if even star already contains even. Because even star is even epsilon union even dot into union dot even and so on. Yeah. So even star already contains even. So that means that if even star is conjugate, then even has to be conjugate.
Yeah.
Necessarily, because even star contains even. So therefore, if even star is conjugate, then even has to be conjugate. Now there is one proposition which we are not writing here, which is intuitively very clear. But if you want to prove, you just need a little bit of time. Just think of an expression like this, okay? Just reduce every other, just forget about all the other guys. You just make them empty. Because you can always replace the star by epsilon. Yeah. If you have an expression like this, you can always make star by epsilon because epsilon is already there in star. So you imagine, let's just consider an expression like alpha 0, beta 0, some even star, followed by a word, which I have only said to everybody else too. Now I have a word. Imagine I have this even is not empty. That means I have a word. Now I can, if I take a word from that one and I repeat it so many times, okay, I repeat it a million times. Then what happens is that this same word is matching with itself. This conjugacy means what? I have on top I have a word, bottom I have a word. I slash it somewhere. This part matches with this one. That's everything matches with this. That's what it is. So if I have if I take a word from even and I repeat it a million times, this same word has to match with. So if I have a word on top, if I have on top I have you, bottom I have v, and so on. So the top portion has to match with the bottom portion. It's like slightly matching. So that means that u and v has to be conjugate. If I take a word from u, that uv from u1, then I can claim that if this even star, if this expression alpha 0, beta 0, even star, this word is conjugate, the whole thing is conjugate, then every pair inside this even star has to be conjugate. That's a key insight here, because I can repeat it as many times, so therefore they have to match. So that means that if I have an expression like this, if I have a sumfree expression, every star inside that has to be conjugate. Only then this will be conjugate. Yeah. Okay. Now that is not enough. It does not guarantee you that just because even star is conjugate, this one will be conjugate. But it is again a necessary condition that it is conjugate with this. Okay, so therefore, this is the first problem we formulate, which is that given a quantitative sumfree expression, E is the star conjugate. And the second one is given a sumfree expression given to E star is the expression. If we solve these two problems, then what we do? You start from the bottom and then you apply this one after another, and then ultimately you will check, you will be able to check conjugacy. So it's just a bottom up procedure. So these are the two major problems we have. We have reduced the problem to just taking conjugacy. If you are given a sumfree expression E, and then you want to check these types of conjugacy.
So if I understand you correctly, so every sumfree expression you can obtain by applying these two closures.
Yes.
And you can apply them in any order. Like first you can apply the monoid closure, then the Clini closure, or first apply Clini and then.
Yeah, that is. Yeah. Okay. Yeah. So all right. So now let's come to this problem. This is the. So I'm not in this talk. I just only focus on this one. Actually, both the ideas are the same. We use the same lemmas, and in fact, this is the easier part, and this is the easier part to understand and state also that without much definition. So that is why I'm just giving this. The part does not use this as a black box, and then concept this. So this is what we are going to function. I'll just make the idea. I'll just get the major ideas in front of this. Okay, so now this is the problem. I am given a set of pairs G. It's just like a very simple automata, just one statement, several loops. Given a set of pairs G, UI, BI is, and where I is a counter are all the pairs obtained by concatenation. Okay. So I have a set of pairs with I could be infinite, because when you build these expressions below, you have very infinite number pairs. So this is what you want to check.
But so UI, BI is not necessarily their conjugate.
No, they have to be, in this case, but in our case, they will be conjugate. Otherwise, this will not be conjugate at all.
Okay. So
And so if G is not conjugate, then this is not conjugate. Why I put it this way is because of this problem. Because the complement of the problem is understood. If you ask this question, if I give you a set of finitely many pairs and ask you, is there a pair obtained by concatenation which is conjugate? That is known as the conjugate case, and that's answer. So it's just like the equivalence problem for rational expressions. If I give you a set of pairs, bunch of pairs, and a regular expression, and I ask you, is there a pair which is identity? Is there a pair UU generated by this regular expression? That is exactly PCP problem. You take every pair of the PCP, write it as a regular expression, you take the star and you ask, is there a pair of the form UU? That's answer. But if you ask, every pair generated by this, is it identity? That is equivalence problem, rational transducer, and that's answer. Okay, it's very equivalent. And in fact, equivalence problem just relates to conjugacy.
PCP is post completion.
Post exponential. Yes, sir. It is just a bunch of pairs, and you just check if the closure contains an identity pair. Okay. Okay. So now, let me just tell you there is one key theorem which solves this. One theorem which solves that first. Okay, so this is a complete characterization of conjugacy. So when are two words conjugate? There is a classic result. In fact, there are only 3 or 4 standard classic results of word combinatorics, and they are all elementary. Elementary in the sense of Feynman. Like, doesn't mean simple. It just means you don't need any prerequisite. They are all complicated. Not complicated. Not very easy to remember either. But they are. You don't need any prerequisite. Okay. So second theorem of relationship. What does it say? It says that U and B let U and B be two words. The following are equivalent for. So I have to begin this. Okay, the first one is U and B are conjugate. Second is U is equal to Z for some Z. And third is U equal to XY, B equal to YX, and Z equal to XY star X. So what does it mean? So if U and B are conjugate, then I know that there is an X and Y so that U equal to XY and B is equal to YX. Now, if I plug in an X here on the right, these two words, and X here on the left here, they will be identical. So this will become XYX, this will become XYX. Yeah. If I take U and plug an X to the right, and take V and plug an X to the left, then UX is same as XV. So this is exactly what this one says. Lyndon-Schützenberger says. In fact, whenever U and V are conjugate, there is a cut, and you will find an X. You will find not just an X, you can put anything X, Y star X, plug in here and plug in here, and they will look at it. Okay. So Lyndon-Schützenberger.
The Z in the third item refers to the Z in the second.
Yes. Yes. It's a free variable. Okay. So this is what Lyndon-Schützenberger says. And it's a the idea is this is the same idea we are going to carry. There is nothing new. The same idea of characterizing that. Okay, so we just need to build on this definition. So we will define for a particular pair UV, we need an ordered pair UV. You will say that is a witness.
So,
and yeah.
21.3 is stating that if user equals ZD for some Z,
Yeah.
the only way this can happen is
Yes.
if U is XY, V is YX,
Yeah.
and Z is of the form.
Yes.
But there's no other way in which this can.
No. Yes. You can have different extents.
Yeah. For some.
Yes. Okay. All right. So now we will call it witness, and we will have this definition. We'll say that is an inner witness. So by the way, if you take this definition, switch U and V, you will get an outer witness, because you will get, if you switch U and V, the same theorem, you will get U will come here, Z V will come here. So whatever was an inner witness will become now outer witness. Okay, so I'll say Z is an inner witness of UV, UZ equal to ZV and S. Z is an outer witness of UV, ZU equal to VZ. Both are asserted by Lyndon-Schützenberger. You state one and then you switch U and V. You will be able to find plugin. So when you switch, what will happen is that Z will become YX star Y instead of Okay, so that is an outer witness. And you will say Z is the witness of UV, Z is either an inner witness or an outer. One of them. In fact, so from this one, you have many things. One, whenever I am given a word to conjugate word, there is an inner witness, there is an outer witness, there are infinitely many inner witnesses, there are infinitely many outer witnesses. Because I have a whole expression here of witnesses. Yes, I take X, XYX, XY, transducer. I have infinitely many inner witnesses. And we will see that this is not the case for Russian. Okay, so now we lift it to sets. So I have.
What did you say? This is not the case for
general sets. When you have only one pair, when you have only one pair, you have both infinitely many inner witnesses and infinitely many outer witnesses. But when we lift it to the sets here, you will see that it is going to be. So witnesses of a set of pairs. So I have a set of pairs G equal to UI, I is in I. And then I'll define Z is a common inner witness. If Z is a common inner witness for each pair. So it's inner witness for each pair. Z is a common outer witness if it is an outer witness for each pair, each outer witness for each pair. And Z is a common witness if either it is a common inner witness for everybody or common outer. You cannot have it. For one, it is inner witness for one. You have to be either common inner witness. Okay? That's the question. Okay. So now, here is an example. Let's take this example ABBA and ACCA. So ABBA has inner witness. So whatever your XY is, inner witnesses are out of XY star X. So here X is A, Y is B. So AB star A is the inner witness. Outer witnesses will be YX star Y. So similarly, ACCA will have inner witnesses. And B has, now if you just take the intersection of these inner witnesses, you will get the inner witness of the intersection. So in fact, you take for every pair you take the inner witnesses and you take the intersection, you will get the inner witness. So P has only one common inner witness, which is AB star A intersection AC star A, which is only B. And P does not have any common outer witness because here it is an A, here it is a C, so you don't have any outer witness. So here we have a set with two elements, two pairs in which we have only common inner witness. And so therefore, this set has a unique common witness. But if you take the set AB, BA and AB, AB and BA, BA, actually this you just take the pair twice and you get this pair. So therefore, what will happen is that every witness of this set will be a witness of this set. Okay. Now that's it's not immediate, but it's not. It's kind of immediately intuitively clear that since it is this is periodic in terms of this, whatever property, whatever witness this will satisfy this will. Therefore, this and a single word has infinitely many witnesses. So therefore, you will have infinitely many internal and outer witnesses for this. And if you take the set AB, BA, and BA, AB, this has no common witness. Why? Because here the pattern is A, B star A, then the inner witness will be A, B star A, here it will be B star B. So there is no word, similarly. Okay, so this is what we summarize, which is that if you have a serious set of pairs, then one of the following is true. Either T has no common witness, or exactly no common witness, or infinitely many common witnesses. Okay? So only 3 cases can happen. Now the thing is that our idea is we are going to compute the witnesses. That is what we are going to do.
You haven't proved this, right? Because you're saying without proof. But you have not proved this.
Oh no, I'm not going to prove this, but this is not very hard. What you do is that all you want to say is that you can assume that if you want to prove it, either it has no common witness, okay, guaranteed. Okay, let's assume that either it has no common witness, or it has exactly one common witness. That will also happen because we have already said cases of this kind. All we have to do is that if there are at least 2, then there are infinity to prove this. And what you do is that if there are at least 2, you will be able to show some periodicity. Okay, there is you will come to that lemma, but when you reach the lemma, you will
No, but
yeah.
there could be 2 by 1 being a common inner witness and 1 being
Yes,
a common outer.
yes.
Even then you will be
Even then you will have infinitely many common internal. A good point. Infinite. So the thing is that there is something called yeah. It's not very hard. Let me just add. It's just yeah. Okay. Now this is what we do. This is our theorem about this. Okay. So what does it say? I have a set G of conjugate pairs. Then the following element. G star is conjugate. G star has a combination in Z. G has a combination in Z. Roots of G has a combination in Z. For the moment, just ignore what is roots of G. Just let's only cover facts. So what it says is that this is just like your our second theorem of Lyndon-Schützenberger, which said that 2 words being conjugate I can equate with finding a witness. It's exactly saying that I can equate G star being conjugate with G star having a common witness. And that itself reduces to computing if G has common witness. And that reduces to actually, you don't need to go all the way to G, you can only take roots of G. Roots of G is nothing but primitive roots, right? You know, but if you have a word which is periodic like that, it's called AB, which was periodic in AB. Yeah, AB, BA, and AB, AB, BA, BA. That was periodic in AB. So roots of G is nothing but you take the roots of every pair. Okay. So you will say if you have a word U power n, then you will say U power n is periodic in U. And there is a theorem which says that there is one root which is primitive, in the sense that there is a fundamental periodicity lemma called finite we call it later. The fundamental periodicity lemma says that whenever a word has 2 periods, then there is a period of length GCD of those 2 periods. Just like
So this 2 to 3, I think, should be kind of.
Actually, 4 to 3, 3 to 1, 1 to 2 to 1 are just 2 lines. Everything is 2 lines.
I mean, even 2 to 3 should be kind of a direction, right? Like G is a subset of G star, so
yeah,
it should follow. But the other direction,
yeah, 2 to 3 is obvious because G star contains G star contains G.
Yeah.
Similarly, G star 2 to 1 is obvious. It just follows from Lyndon-Schützenberger because if every pair in G star has a common witness, then by Lyndon-Schützenberger those are conjugates or therefore G star. Yeah, 2 to 1 is obvious. 3 to 2 is kind of if G has a common witness Z, then I can use that just like like if I have U1 V1, U1 Z equal to V1 Z V1, U2 Z equal to Z V2, then if I have U1 U2 Z, then I can use U2 Z to switch. Yeah, like so if I have U1 Z equal to Z V1 and U2 Z equal to Z V2, then if I have U1 U2 Z is nothing but U1 Z V1 equal to Z V2 V2, yeah, just applying indexation. Like if U1 V1 and U2 V2 have both Z, it's like using Z to commute. Z commutes. One way to see if the Wheatons commutes with not commutes but transforms. Okay, I'll just get it. Okay, so what is roots? You will in a couple of definitions. A word is primitive if it cannot be expressed as a power of number. Or is it ABA is a primitive word, but AB is not. ABA is primitive, but AB can be expressed as AB square. Primitive root of a word U is a primitive word for U such that U is equal to rho U for N for some N plus 1 and it is unique. AB is a primitive root of. Okay, that's a primitive root. Now, roots of P is a set of all primitive roots of each parent P. So, roots of the set ABBA, ABAB. This is all like you take, if I have this set, this 2 has the same primitive root ABA. This is the ABAB, that is a primitive root. It's also you take this. Why are roots important?
Sorry, could you go through?
Yeah.
So what is
So, roots of P.
the set?
Roots of P, you take all the primitive roots of every pair and P. That's your roots. Okay. Now, why are roots important? Because roots make our life easier. Because in the beginning, we observe that whenever you have a pair UV, there can be several cuts. But the thing is that whenever you have a conjugate primitive pair, a primitive pair that is conjugate, then it has a unique cut. You cannot have more than one. Because the reason is, imagine U and V has 2 non-empty cuts, x, y, and x prime y. And this is a typical kind of argument. We just want to a typical kind of argument in combinatorics words. So imagine you have 2 cuts for U. One cut is x, y, another cut is x prime y, right? And we know that x and x prime are ones. Now, without loss of generality, let's assume that x prime is equal to x of x. Then there is a P such that x prime P is equal to x. Yeah, there is a P such that x prime P is equal to x. So therefore, I can write B as yx, which is same as y x prime P, because x is nothing but x prime. And similarly, I can write B as y prime x prime, which is nothing but P y x prime. So what I have written is, we have written B as 2 words, a concatenation of 2 words, y x prime and P and x prime. Now there is a theorem, first theorem on Lyndon-Schützenberger says that 2 words x and y commute if they are power of the same. If I'm reading the power of the same. Like the 2 words can commute only if they are of the form u power m and u power n. Only then they can. Otherwise, they cannot. So therefore, this what we have just done is that we assume that UV is conjugate, and we have two distinct cuts. Then we said that U and V is not. So therefore, this cannot happen. So we have to be. Now, why is this useful? Why is it useful? Because basically, what we are going to do is that we are going to take a long word and you want to slash it somewhere. You want to say, argue that, look, I can find a weakness. Yeah. Now, where all that cat can happen. If I take a long word, where all that cat can happen. We want to have some handle on where the cat can happen. So that is why we assume that we can write it in terms of this primitivity, and then we know that where all possibly the cat can happen as appealing to this.
Sorry, I think I missed. What do you mean by commutes here?
Commute meaning that xy equal to yx, like here.
Okay.
So v is equal to yx by v, and v is equal to v by x by.
Okay. I see.
So
I see.
So now these 2 arguments we will formulate as a 2 lemma. One is called cut lemma, which is that a primitive word cannot be equal to if it's not trivial sequential. So yeah. Alright. So now one of the so this is what I was repeating. Like if I take a word UV and I repeat it so many times, and what all cuts there can be, because I don't know anything about UV, but appealing to the previous lemma, I know that okay, U and V, if I know that U and V are primitive, then I know where all that cut can be, because I know that they cannot match it to any other non-trivial way. They don't match exactly at the boundaries of x and y, then they will lead to an extra cut, which is not possible. So therefore, it just tells me that whenever U and V are primitive, U power and V power, any cut is of x star x and y star. All right. So that is the idea about Okay, now, so from this you will get for all this, like, there is a weakness of AP, if and only if there is a weakness of OB, and if there is a weakness of exact G, there is a weakness of K. Let's not know that because it's not obvious, like, you still need a couple of sentences to argue them. Now there is another lemma also which we use for our case analysis, which is that if G star is conjugate, then all probability pairs of equal length in G are either xi identical or yi identical. I'm not going to do this, but yeah. This is the case like AC, the case like AB, BA, and AC, CA. Yeah, they are primitive pairs. So the only like AB, BA, and AC, CA, they will match. Like B will match to B, C will match to C, and so on. AB, BA, and BC, AC, CA. So they are conjugate primitive pairs, but they are primitive. Then in that case, one of their components up to B is the same. That's what it is. Okay, so now, so how does it happen? So 4 to 3 is just parallel lemma we just, so 3 to 2 is what I just wrote there, just like a train. You start plug a result there and then start switching. Okay. And then G star to G is and 1 to 4 is what the non-trivial part. Okay, and so how do you do the non-trivial part? This is what we have to do. The non-trivial part is, yeah.
2, 3, 4, it's the same state which is a common weakness.
Yeah. It's a trivial, yes. So how do you do this? That if G star is conjugate, then rules of G star. So the idea is that there is no intelligent intelligence involved. You just take you have an infinite set, but you start with a finite set, and then you say that if I have finitely many pairs, if every pair generated by this is conjugate, then they have to be they have to have a common weakness. That is, you just have to go and okay. And but you will use these lemmas, that lemma and equal lemma, and you will use these ideas like primitivity to argue that okay, if the cut happens in the beginning, or if the cut happens in the middle, if the cut happens towards the end, or if yeah, so we will argue that. And here this is the periodicity lemma which I was talking about. Yeah, again, right? The biggest thing we are going to do is the appeal to this is find this fundamental periodicity lemma. It says that whenever I have a word, so this is for matching in the middle. You can also the standard finite will talk about a word having two periods, or two words having a common prefix. But you can have, for us it is more easier if initially we started working with the prefix, and then my student found this and this made our life more easy. So for any two words U and B, U for omega and U for omega have a common factor of at least U B of this, then the primitive rules of either functions. And if you're talking about instead of factor, if you're talking about the prefix, then what it's going to say is that U and B, the primitive roots of either are the same. Okay. So now that you are matching in the middle, it will be only conjugate. If you're matching in the beginning, if U for omega and B for omega have a common factor of length U plus V minus GCD of UB, then primitive roots of U and B are the same. That's what finally this original state of finite.
So okay, so why do you need infinite words here? I mean, you could have considered some finite.
Yeah. So there are two ways. Two ways you can talk about finite. Fundamentally, finite is about I have a word and I have two periods. Let's imagine I have two periods. I have a period of length, let's say 12, and I have a period of length 4. What finite is going to say is that actually there is a smaller period. Okay? Actually, there is a smaller period, and that period is nothing but the GCD of 4 and 12. That is what finite is. Now, if I want to talk about, let's say, instead of talking about two periods, because basically what we are saying is that this is actually two, and it is what the two periods. One is new, one is new. Just splitting that same statement as to the same, because we are talking about pairs of words here. So in fact, that is why we use this version instead of the word having two periods. This is more amenable for our use.
So then what does common factor mean?
Common factor means continuous subword. Like I have this U for omega, V for omega. At some point, if there is some factor, like they are going to match like this. They are going to match like this, yeah. if there is some factor of this word such that they are the same.
So the contiguous segment in u bar omega and v bar omega must be lined up.
Yes,
Okay.
yes.
No, they are they aligned or they may not be aligned?
No, they are aligned now. U bar omega and u bar. There are two words, u bar omega and u bar.
So this common part you were saying they start at the same position in both u omega and v omega. They start at the same position.
Yes. Some. So just means. Okay. Yeah, actually, the standard terminology is always the problem. Factor means whatever contiguous subword. Subword means like as a substructure, like subgraph. You don't take contiguous. So in the words also, factor means contiguous subword.
No, my only confusion was about, like, for example, suppose you want these two to have a common factor of length 100.
Yeah, you are talking about like
can it be
yeah. Then it doesn't say anything. Okay, so now this yeah. So basically, yeah, this person can okay. So what you do is that yeah. So this is the idea. So you imagine you have some d pairs. You do it for finding pairs. If you have some pairs, u1, u1, v1, ud, vd. You consider this word u1 star, v1 star, u2 star, v2 star, ud, vd star. Okay, it's a long word. Lot of u1s, lot of u2s, a lot of u3s. Now the cut happens somewhere. When the cut happens somewhere, what will happen? It will start matching. Yeah. So some u1 will match depending upon where the cut happens. Some u1 will match to some vj. U2 will match to some vj plus 1. And now, since we have taken two long words, what will happen? We can apply finite will and we can get that look that u1 and vj has are conjugates. Yes. If I take this long word and I slash it somewhere, so it's like on top I have these, on bottom I have these. So u1, u2, u3, u3, and so on. u1, u2. Cut somewhere. Then what happens? Whatever. So if I'm cutting like this, you just go ahead. So if I have v1, v1, I'm sorry, u2, u3, v1, and let's imagine I cut here. Okay, I cut here. This is the cut of this one. That means this is X, this is Y, and this is somewhere some cut happened. So this is Y and this. That means that this is going to match with this person, yeah, and this is going to match. When I do that, this U2 will start matching to this U2, and this U3 will start matching to this U2, and so on. And this will match to this. That means that by applying conjugate finite, I'll be able to say that this U2 and this V1 are conjugates. This U1 and this are conjugates. So then I'll get a bunch of I'll be able to say that look, a lot of their primitive roots are conjugates. So this is the way. So that's what I'm saying. There's no it's an elementary idea. So then you will get these pairs are conjugates. So this way you will be able to say that for a finite set of pairs, by just examining one word and the fact that it is conjugate, you will be able to say that these guys are conjugate. Now, what do you have infinite set? Now, how do you do that? Now you need a compactness argument. Again, this is not hard. What is this compactness theorem? We say that. What does it say? It says that if G is an infinite set of pairs, if every finite set of G has a combinator, then G has a combinator. Okay, so what's the idea? The idea is again going back to the first theorem, the first thing which we noticed that either three cases can happen. Either there is no common witness, or there is exactly one witness, or there are infinity witnesses. And if there is exactly one common witness, then whenever I take two sets, their witnesses have to be the same. Otherwise, the new thing will not happen. So it's not a deep statement. It's just observing that because of this, this thing holds. And then you can complete the proof. You say that every finite subset you can argue that it's a common witness, and then using compactness. Yes. Okay. So this finishes the direction from 1 to 4. That's the idea. Okay. These are conjugate relations of theorem.
Is this the theorem that justifies the definition of common witness, or does common witness appear?
No, common witness.
Yeah.
No, we have never. We haven't seen the notion of common witness to sets. We have seen for I think we introduced. I think this. I haven't seen it.
Yeah, then it's no. If the definition is unclear, why the definition? This theorem is what actually justifies the.
Yes. Yeah. But the idea of a common witness, I think that should be there. Like in this context, we are saying purpose. The idea of
No, why is common witness and no, I understand. Follow the definition. Why is it even as a sequence of things? Why do we care for a common witness? Why is a common witness a useful object? Why would one want to study?
I mean, so
this definition, this theorem makes it clear why one would like to look at common witness. But otherwise, I don't see.
well, otherwise, how do you compute? You need
for
a
the decidability.
for the decidability. You want to check in the relations.
Like whether it's a conjugate. The
You
same
want to
conjugate.
at the end of the day, you want to compute it bottom up. Yeah, you are given a rational expression. You want to compute it bottom up that all the stars inside are common witness. And
No, that we are using this theorem. If I didn't know this theorem, why is common witness a useful fact?
yes.
Statement of the definition, then I don't see why it's a useful definition at all. This theorem is what justifies us to study this notion at all.
Yeah.
That's all I say.
Yeah.
Yeah.
Okay. So now therefore, and you do it for the other case also for the monoid process. It will have an extra. It's a bit more hairy. That's all. The ideas are pretty much the same. And interestingly, this does not generalize to arbitrary expression. This theorem is only hold for sumfree expression. So it seems like this reduction which we make in the first step, reducing maximum expression to sum of sumfree expression is kind of okay. Alright, because AB star, BA star, and BA star does not. These are infinite conjugate set, but does not. Each individual one has this, but okay. So now this is
So given an arbitrary expression, you can always convert it into the
some of and each one of them, if it is conjugate, each one of them will have a conjugate, but in general they may not have. Okay, so given a sample, this is the decidable part. Given a complete expression, common witnesses can be computed in time or h time q, where it is the start of the expression and n is the end of the expression. Now, let me just quickly comment on a couple of applications and what is our motivation to study this problem with conjugacy. Okay.
So it started with this monoid, right?
Yes.
So in the complexity when you were talking about this,
So it's just the regular rational expression. You can think of it as a rational expression. You just compute in size.
okay, but the side of the rational expression has some dependency on the side of the monoid.
No, monoid is of course infinite.
Because
Because it's the entire set now. Like it's a set of this. So monoid is infinite. You just take individual word, individual monoid elements will be a word. Okay, so what are the applications? So one, conjugacy has been used in the transducers a lot. Why? Because this is a very well-known problem, which is that I give you a non-deterministic transducer. And non-deterministic transducers are used in a lot of these, whenever you have synthesized analog signal to digital signal conversion. You sample it, now you get a sequence of signals. And now you want to aggregate these individual signals and you want to construct outcomes. Yeah? For example, if it is digital audio signal, you want to convert it into phonemes. Or if it is like individual letters, you want to convert them to words. And this is the level where you use a lot of weighted. And weighted automata, these are inherently non-finished. Because eventually what they are going to do is that they are going to compute a probability. Okay, this signal has this weight. This concept has this way, this concept has this way, and so on. Now you look at, you don't throw away everything, you just look at, in totality, you look at this thing and you decide what is one to choose. That is how it works. Okay. So this is a very well-known, which is, I give you a rational transducer. Does it determine, can you determinize it? Is there an equivalent deterministic problem? And Shofu gave an answer in 1977. And he said that a rational transducer defines the sequential function with this twinning. Now what is twinning? Twinning means that if I take a
sequential function.
Sequential function means that it can be done by a deterministic automata.
Okay. So a deterministic transducer is the same as a.
Yeah. Yes. I mean, the beginning and end, there is always. Yeah. In the beginning and end, you can append something such also. It doesn't matter. Yeah. So what is T? So if I have a clean transducer, if I have a transducer T in which I have erased all the unreachable sites which cannot reach my assets upon. Okay, and I can square that transducer. Square in the sense that I can, because it's a deterministic transducer on an input where you can have multiple ones.
And tree means something which is deterministic and
Deterministic, yes. Okay. Not like that. Yeah. You remove everything which is unknown. Which is unknown. You cannot, not useful state. You remove everything which is not useful. Because T is a non-deterministic transducer. It's not deterministic.
Okay.
Yeah. I'm saying that a rational transducer T defines a sequential function. It is true.
No, you are talking about tree.
Yes, but when I talk about this T, this is a rational transducer, which is a non-deterministic transducer. And this one, T need not be deterministic.
Okay.
Okay. But what T contains only useful and useful states, in the sense that every state is reachable and every state is for reachable.
Okay.
So if I am given such a transducer, I'll say state P and Q of T as tree. If I take the square of T is you take product of T with T and look at pairs which are reachable by the same input word. That is what is, you look at such words. Okay. So you take T, you take this square, and you look at every pair of states which are reachable by the same input word. What it says, so it produces two different output words on the same input. Now, obviously, they have to be the same. I mean, but up to some delay, they have to be the same. Like one, because otherwise, this automata will output two output words. Then it cannot be sequential. So it will output the same thing, but some will be ahead of that is what we call delay. That delay is exactly what you will get when you take the loop from PQ to P. This is what training is. Okay? And this is what you will. Now, this property is not finitely stated because you can take it in any way. What Shotru did is that he said that, okay, look, this property is infinite because it involves something, but it is enough to check for n square many length words because n square will be n square will, and it once if it is possible to do it for n square, then it will be for n infinite. And then similar characterization exists for finitely sequential and function. And these proofs are so this property, the decidability comes from these clever arguments. Okay. Now the thing is that in our decision procedure, you don't need this cleverness. You can just say that, look, okay, this is what you have to compute. You take that state, you compute its rational function, you compute its sequence, and check it. So you can replace all these clever arguments by very dumb computation, but with a higher complexity computation. Okay. So that is one thing. That means that you get a uniform decision procedure for all these kind of characterizations. You don't need any cleverness, but you will have to pay some price. You have to pay some higher compensation. Okay, this is the one application.
So sorry, so U and V here are the outputs, right? And there's a saying that U and V there is a delay.
Yes.
So one is a prefix. No, so okay. So one is a shift of the other.
Yes, yes. So whatever you get in that loop,
yes,
that delay is exactly what is lacking here.
Okay.
But there can be several. Yeah. So now you want to say that all these things, if you look at the rational relation defined by PQ to PQ, that's an automata which produces these pairs of words, which is an output relation, output rational relation. That has a common weakness. That is exactly what is this. All right. Now another thing is, this is what our motivation was. So what is this idea? Okay, I'll be done in 5 minutes. Okay. I think we started 10 minutes later. 5 minutes. So this is what our main motivation is, which is that functional equivalence for transducer is decidable. In the sense that I give you two transducers and ask you this question, do they define the same function? It is decidable. Okay. Now let's imagine that I give you two transducers which are not equivalent. But I have 3 transducers and I can ask you this question, which one of them are closer? Which one of them are more closer? Okay. Now how do you argue that? How do you measure that? On any input, the respective outputs are approximately convert one output to another using PUD. So what's the idea? For instance, you take a word. For instance, it's been measured in D of U equal to 0. Otherwise, it's 0. Having this D of U is minimum number of letter to letter substitution with the conversion. Levenstein LGC. minimum number of insertions, deletions, and substitutions which you require to convert from unit. So you have this word matrix, okay, and you have quite a plenty of them. Conjugacy distance, transfer distance, log and common substitution, normalization. Imagine I give you a word metric. I give you a metric on words. I can list it to transducers. I define the distance between transducer T1 and T2 to be supremum over the distance between their output words. Okay, if their domains are the same, if the domains are different, I'll put it to infinity. So now what does this D measure? D measure on any input how much their output can be. Yeah, how much their output can be. And we can say that T1 and T2 are close if D of T1 T2 is finite. And T1 and T2 are K close if D of T1 T2 is at most.
I mean, if the domain is different, then I would have defined it as undefined also.
Yeah, it can be different, but it's just to make it a metric. Yeah. Just to make it a metric. Okay. So now, here is an observation. You can compute the distance on a metric if and only if you can decide this closeness and K closeness. Okay, and this is not necessary, but my point is simply this that this is the observation that two transducer circuits, that means they're on any input their maximum distance between their output is bounded if and only if all cycles in the Cartesian product are conjugate. That again requires an proof. So now what it means is that since we know how to check this, whether given an automata, the product of automata, whether their loops are conjugates, that's something we can check using this idea. And therefore, you can verify closeness, and therefore, what it's saying is that all these metrics you can compute on transducers. That means that we generalize recurrence problem to almost pretty much all word metrics. You give me two word transducers, two non-zero transducers, I can compute, or two functional transducers, I can compute the functional transducer, I can compute this. So that will be very useful because I give you two spell checkers and I can ask you like to how much do they differ to grammarly if they are transducer. Okay, so now this is also we have in mind, which is similar. Okay, that's
Questions? If there are no more questions, thank you.
okay. Thank you for everybody watching the fair part. I forgot.